Hello friends, this is Hasiba. Welcome to today's session on queuing models. So far under queuing models, we have discussed about the definition of queuing model, what are the different characteristics of queuing systems like the calling population, the system capacity, what is the queue behavior and queue discipline. Under queue behavior, we have studied three types of queues, that is bark queue, renage queue and jockey queue, right? And under different types of queue discipline, we have discussed about FIFO, LIFO, priority queue and other types, right? And the next characteristics of queuing system is server utilization. And finally, today's session we'll be discussing about what do we mean by queuing notation, what are the different long run measures of performance in a queuing system, and also what do we mean by networks of queues. So let's start today's session by understanding what do we mean by cost in a queuing problem. Cost can be associated with different aspects, right? So for example, cost can be associated with respect to the waiting line or the number of servers in the queuing system. So the system incurs a cost for each customer in the queue, say for example at a rate of $10 per hour per customer, right? So for any customer who is waiting in the queue, let us say, right, so the cost is $10 per hour per customer, right? So the average cost per customer is given by, the formula is sigma j is equal to 1 to n, right? So 1 to n is the number of customers. So for every customer we have $10 into w of j. W of j is nothing but the waiting time of the jth customer in the queue, right? So wjq is nothing but waiting customer of the waiting time of the jth customer in a queue divided by the total number of customers, right? So like this we can have a formula to find the average cost per customer. So we have different notations for parallel server, right? So Pn is nothing but the steady state probability of having n customers in a system, and Pn of t is nothing but the probability of n customer in the system at time t. Lambda is the arrival time, lambda e is nothing but the effective arrival rate, mu is service rate of one server, delta is server utilization, an, capital An is inter-arrival time between customer n minus 1 and n, Sn is the service time of the nth arriving customer, Wn is the total time spent in the system by the nth arriving customer, right? So Wnq is the total time spent in the waiting queue by the nth customer. L of t is the number of customers in the system at time t. Q of t is the number of customers in the queue at time t, and capital L is nothing but the long run time average number of customers in a system. LQ is long run time average number of customers in a queue. W is long run average time spent in the system per customer, and WQ is long run average time spent in the queue per customer. These are the different notations which are used in the parallel server. You need not remember this, right? So just you have to understand. So if at all I say mu is nothing but the service rate of one server. If it is delta, it is server utilization, right? So like this, whenever you see the variables, you should be able to correlate the meaning to this particular table, right? So the same way we have some notations for parallel servers, right? So those notation we call them as Kendall notation, right? So for example, for a sample system I can just write it as m/m/1. That means customer service desk in a store, right? So if at all it is m/m/1, that means it is an example of a simple system, right? Simple system, right? So for example, customer service desk in a store, right? So you have a service desk for a customer in a store. Multiple server, we denote it as m/m/s, right? So example is airline ticket counter, right? So if I take constant service, it is denoted by m/d/1, which is example is automated car wash. General service, it is m/g/1, example is auto repair shop. For limited population, it is m/m/s/infinity/n. It is an example is an operation with only 12 machines that might break, right? So these are also different commonly used queuing system, right? So it is not important for examination point of view, only you should know that what are the different types of queuing systems available. The next very important topic is queuing notation, right? So since there are so many different types of queuing system, Kendall proposed a notational system for parallel server system. So the format for queuing notation is given by A slash B slash C slash N slash K, right? So this is the format for any queuing system where capital A represents the interarrival time distribution, B represents the service time distribution, C represents the number of parallel servers, N represents the system capacity, and K represents the size of the calling population. Size of the calling population is nothing but the number of customers, right? So the general format of any queuing system is A slash B slash C slash N slash K, right? So A is the interarrival time, B is the service time, C is the number of parallel servers, N is the system capacity, and K is the size of the calling population. And the common symbols for A and B include M, right? So M is nothing but for your exponential or Markov distribution. Whenever you are using exponential or Markov distribution, we write it as M, right? So D is nothing but it is constant or it is a deterministic type of a system, right? So constant or deterministic. EK, if I write, it means it is an Erlang distribution of order KS. PH is nothing but it is a phase type distribution. H is hyper exponential distribution. G is arbitrary or general type of distribution. G1 means it is general independent distribution, right? So this is very, very important topic repeatedly asked in your exam as to define queuing notation. So if they ask queuing notation, you have to write the format and you have to explain each and every variable and what are the common symbols for A and B. Next, the last topic what we have is long run measures of performance of a queuing system. That means what are the different measures which are used in order to estimate the performance of the queuing system. So the long run measures of the queuing system are long runtime average number of customers in the system, that is L, right? So Q is nothing but LQ, long run average time spent in the system, W, the Q which is WQ per customer, server utilization or proportion of time that a server is busy, which is P, right? So all these are the different variables which you have already seen, right? So here, right? So in the notations of parallel server, we have seen, right? So few of those variables we'll be using in order to determine the long run measures of the queuing system, right? So these 5 variables are called as the long run measures. So runtime average number of customers, the Q, the long run average time spent in the system, which is a W, the Q, WQ per customer, the server utilization or proportion of time that the server is busy. Other measures of performance of interest include the long run proportion of customers who are delayed in the queue longer than the time unit. Next, the long run proportion of the customer who are turned away because of capacity constraints, right? So we can have the number of customers who are delayed and in queue longer than the time, that means people are waiting in the queue more than the time unit, right? So that is called as the long run proportion of the customer who are delayed in the queue longer than to the time unit. Next, we have the long run proportion of the customers who are turned away because of capacity constraints, right? So due to some capacity constraints, we can have the number of customers who are waiting in the queue and finally they will just leave the queue and go. That is called as they are turned away. Next, we can have the long run proportion of the time the waiting line contains more than K naught customers, right? So if the waiting line has more number of customers more than the limit of the customers, right? So then also we can estimate the measures of performance, right? So the measures of performance for general system is given by G slash C slash N slash Q queuing system, right? So and this particular system is considered here for discussion. That means using this particular queuing system, which is the general queuing system, we are discussing how to calculate the time, which is nothing but the average number in the system L. So consider a queuing system over a period of time T and let L of T it refer to the number of customers in the system at time T. So let Ti denote the total time duration in which a system contained exactly I customers, right? So sigma C is equal to 0 to infinity, Ti is equal to T. So this is the time weighted average number. So it is denoted by sigma C is equal to 0 to infinity, Ti is equal to T. That means we have to add all the different time intervals within the particular duration of time, which is 0 to T, right? So which is equal to your capital T. So this is these are the few formulas for a total area and all, right? So you need not study this, right? So just remember how to calculate the average number in the system L, right? So just it is nothing but the summation of the individual times which are spent by the customers in that system at time T, right? So the same way we have average times spent in the system per customer, which is a W, right? So the average system time is given by the formula W cap is equal to 1 by N, sigma I is equal to 1 to N Wi, right? So next we have something called as the conservation equation, which is L is equal to lambda W, where L is the queue length, lambda is the arrival rate, and W is the waiting time. Next, we have the server utilization. So server utilization is defined as the proportion of time that a server is busy, right? So server utilization is nothing but for what amount of time the server is busy. So observed server utilization is denoted by row cap, and it is defined over a specified time interval, right? So all these are different formulas, right? So row cap is nothing but your row cap is directly proportional to rho. Rho is the server utilization, and observed server utilization is given by rho cap as t tends to infinity, right? So these are the different types of server utilization which they are calculating for the two types of queuing system, which is G/G/1/infinity/infinity queue, right? So this is same like your queuing model where we have A/B/C/N/K, right? So infinity means number of customers is infinity, calling population is infinity, and G is your general queuing system, that is arbitrary queuing system, right? So the last topic here which is important is the steady state behavior of M/G/1 queue, right? So the steady state solution of the number of queuing models are solved mathematically. For the infinite population, the arrivals are assumed to follow a Poisson process with rate lambda arrivals per time unit. That is, the inter-arrival times are assumed to be exponentially distributed with a mean of 1 by lambda. So the queue discipline will be FIFO. So these models are also called as Markovian models. The M/G/1 queue models are also called as the Markovian models, right? So we have few notations here, right? So for the server utilization for L, W, WQ, LQ, and P naught, right? So this table formulas you have to remember, right? So server utilization is given by lambda by mu, right? So L, which is the long run measure of performance, is given by rho is equal to lambda square into 1 by mu square plus sigma square divided by 2 into 1 minus rho, right? So which will be equal to rho plus rho square into 1 plus sigma square mu square divided by 2 into 1 minus rho, right? So W is given by 1 by mu plus lambda into 1 by mu mu square plus sigma square divided by 2 into 1 minus rho, and WQ is lambda into 1 by mu square plus sigma square divided by 2 into 1 minus rho. LQ is given by, it is same as the previous one, which is lambda square into 1 by mu square plus sigma square divided by 2 into 1 minus rho, which is only rho square into 1 plus sigma square mu square divided by 2 into 1 minus rho. What is P naught? P naught is given by 1 minus rho, right? So like this you have a different formulas in order to calculate the steady state parameters of M/G/1 queue. This is repeatedly asked exam question. Write the define the steady state behavior of or steady state parameters of M/G/1 queue, right? So then you have to explain all this. The previous topic, which is to find out the server utilization and long run measures of performance, right? So all these derivation, right? So they are rarely asked, but the most important is the about the steady state behavior. You have to remember all these formulas. And the last topic what we have here is the networks of queues. So what is networks of queues, right? So in many systems they are naturally modeled as network of a single queue in which customers may be departing from one queue, they may be routed to the other, right? So a network of queues, right? So that means queues and queues within a queue, right? Or we can say collection of queues, we can call it as a networks of queues, right? So as dealt earlier, the study of a single queue, the following results assume a stable system with infinite calling population and no limit on the system capacity. So under network of queues, we have that provided that no customers are created or destroyed in a queue, then the departure rate of a queue is the same as the arrival rate into the queue over the long run, right? So no customers are created or they are destroyed in the queue, right? So if no customers are destroyed in the queue, then the departure rate, that is people going out of the queue, is same as the people entering the queue, right? So the departure rate of the queue is equal to the arrival rate of the queue over the long run. If at all the customers are arrived to the queue at a rate lambda I, and a fraction of 0 is less than or equal to P naught is less than or equal to one of them are routed to Q J upon departure, then the arrival rate of Q I to Qj is given by lambda I Pij over the long run, right? So that means if the customers arrive at one Q, right? So the Q is Qi at a rate of say lambda I. Customers are coming to one Q, which is called as Qi at a rate of lambda I, and few of them are routed to qj upon departure, right? So after leaving qi, they are going to one more queue, which is qj upon departure. Then the arrival rate from qi to qj, that means people moving from qi to qj queue is given by lambda I into rho ij over the long run. Next, the overall arrival rate into Qj, which is lambda I, it is the sum of the arrival rates from all the sources, right? So the overall arrival rate into the Qj is given by lambda j is equal to Aj plus sigma all I lambda j into Pij. Next, we have if for each Qj arrival from outside the network from a Poisson process with the rate Aj, then is lambda if there are Cj identical services delivering exponentially distributed service time with mean of 1 by mu j, then in the steady state, right? So Qj behaves like an m slash Cj queue with arrival rate of lambda j is equal to Aj plus sigma all I lambda I Pij, right? So these are the 5 important points which you have to write when they ask the network of queues, right? So queues, collection of queues, right? So which are interconnected to each other. Collection of queues which are interconnected to one another, we call it as the network of queues, right? So under network of queues, we have few points to remember. That is, no customers are created or destroyed into the queue. If one customer is arriving to one queue and he is going to one more queue, then what is the arrival rate of the particular customer? So what is the overall arrival rate of a particular customer into qj? Next is last point is, if at all for a qj, if the arrival is from outside the network from a Poisson process, right? So then how do you calculate the arrival rate in the steady state, right? So this completes your queuing models, which is the second half of your second module. Thank you.